So I'm going to start with sp cubed, since we already talked about that a little bit. How are you going to know if a central atom uses sp cubed hybridization? The key is to look at its electron geometry. So for sp cubed, that will fall under tetrahedral electron geometry. We see this with molecules like methane, so CH4. And there's all single bonds. When you have a single bond under the hybridization system, that's going to be known as a sigma bond. So here in our example of methane, we have 4 sigma bonds. Orbital types. So in this example, we're just going to have sp cubed orbitals. So we have 4 sp cubed orbitals or hybrid orbitals. And then we're going to have 4 single or sigma bonds. And let me make a note about the sigma bonds. So this is sigma, and I think of the S's. So sigma starts with a S, and single starts with an S. You might be wondering a little bit about hydrogen. So I'm drawing methane, and you're like, okay, I can envision a carbon at the center of this over here. And we have our 4 sp cubed hybrid orbitals depicted. And they all have that tetrahedral orientation with respect to one another. Hydrogen doesn't hybridize. It doesn't really need to. It has one half-filled orbital naturally. So I'm going to keep hydrogen as a 1s orbital. And so there's going to be overlap with each of these hybrid orbitals and the 1s orbital of each hydrogen atom. The sp cubed part is this part. In our second example here, for sp squared, let's look at another familiar molecule. Let's look at formaldehyde. So carbon double bonded to an oxygen with 2 hydrogens. I specifically chose this molecule because it has a trigonal planar shape around the carbon. And that's going to be the geometric family. You can identify sp squared hybridization if you know that you're looking at a trigonal planar central atom. So sp squared. So if I put in the one that's understood and I count that up, 1 plus 2 equals 3. So that means 1 s orbital and 2 p orbitals came together. That gives me a total of 3 hybrid orbitals. 3 sp squared hybrid orbitals. That's a little bit concerning because we still have 4 bonds. We still have 8 electrons. If we just have 3 orbitals, we're only talking about 6 electrons. So in the example of sp squared, we also have unhybridized orbitals. So we have 1 standard p orbital involved. 3 plus 1, now that's going to get us to the 4 orbitals altogether that we need to explain how carbon completes its octet. In our drawing here, in our picture here, we can see the hybrid orbitals. So this lobe is an sp squared, and again, I would expect there's like a little piece on the back, a little spherical piece, but they leave that out because it gets hard to draw. So 1, 2, 3. Those 3 lobes represent the 3 hybrid orbitals. Now, we can label those, or those hybrid orbitals are going to participate in sigma bonding. So for instance here, with one of the hydrogens, this overlap between the hydrogen and the sp squared, that's sigma. And we could also label it sigma over here. It's a single bond. That happens here as well. So that's another hydrogen in its 1s orbital. And there's an area of overlap. And that end-to-end overlap is a sigma bond. We have oxygen. I'm going to put oxygen in an sp squared orbital as well. And we'll get into that a little bit more in future lectures. But because we have limited space here, the part of the oxygen that I want to talk about. So we have an sp squared situation with our oxygen. That's an O in the middle. And this, I'm trying to depict a trigonal planar arrangement with the 180-degree bond angles. You might be a little bit better at drawing this. So we have carbon with sp squared, oxygen with sp squared. There's the first bond between carbon and oxygen. That first bond is still a sigma bond. So in the formaldehyde, we have 3 sigma bonds. So sigma bonds are single bonds, but they're also the first bond in a double or a triple bond. And at the end of the day, the sigma bond is this end-to-end overlap. Now, this is linear between the carbon and the oxygen, and it's linear here. But we need to create that second bond. So we have our unhybridized p orbital. I'm going to draw it in red. And this is a plane. Perpendicular to the plane, we'll have our unhybridized p orbital. And I'm drawing it like dumbbell shaped. So carbon will have 1 p orbital. I know it has 2 lobes, but remember p orbitals have 2 lobes. And then this is the p orbital of the oxygen. And then we create that second area of overlap by doing side-to-side overlap. So the electron density is shared from the sides. I'm drawing 2 areas where the sharing could potentially occur, but we're still just talking about one more bond. It can occur on either side. I know this is a lot. This side-to-side overlap is known as a pi bond. To summarize a little bit, we have sigma bonds which occur when we have end-to-end overlap and it's usually between hybridized orbitals. The main exception, I would say, would be some of the group 7s and our hydrogens. We have the end-to-end overlap between a hybridized orbital and an s orbital or a p orbital. We're going to see all these different examples. But here's the classic end-to-end overlap between two hybrid orbitals. One hybrid orbital of the carbon and one hybrid orbital of the oxygen. This is going to be your first area of overlap. So your single bond, because that's the first area of overlap, or the first bond, it doesn't matter which one it is, but the first bond in a double or triple bond. Then we have pi bonds. And pi bonds are the side-to-side overlap of unhybridized orbitals. The pi bonds occur in double and triple bonds. The first bond is going to be a sigma, but then after that, the second and third bonds will be labeled as pi bonds because they're side-to-side overlap. Last thing here in our picture, oxygen has two lone pairs. And we can throw lone pairs into hybrid orbitals. That's totally permissible. So one of the hybrid orbitals on the oxygen overlaps with the hybrid orbital of carbon. Then we have two hybrid orbitals to hold the two lone pairs. And then finally we have the p orbital, which accounts for the double bonding, the side-to-side overlap. Next up, sp. So you're going to see sp with any of the linear electron geometries. I threw in the ones there. It's the combination of one s orbital and one p orbital. 1 plus 1 is 2. So at this point we have two sp hybrid orbitals. This is an sp and this is an sp. And we see the nice linear shape. So again, let's do a carbon compound. We'll do carbon triple bonded to another carbon. And in order to do that, this is just one of the carbons. So, and it's occupying an sp. So we're going to have a second carbon also using an sp. This comes down to the shapes. If you were to analyze this for shape, you would tell me, oh, it's got a linear electron geometry. And that's how we know it's sp. Then you come over here, you're like, that's linear too. Well, then that's also sp. So I'm going to draw another carbon. And let's get that sigma bond in there right away. So between the two sp orbitals, we have end-to-end overlap right in there, and that's a sigma bond. We can throw in the hydrogens. I planned poorly. There's a hydrogen off the page, but at least get this hydrogen over in here. So that's right there. That's another sigma bond. We have end-to-end overlap between the sp and the 1s of the hydrogen. Now, carbon, any carbon in this atom has 4 orbitals, or it needs 4 orbitals to hold those 8 electrons. Right now we only have 2 orbitals. So for sp we have 2 hybrid orbitals and then 2 unhybridized p orbitals. These pictures get messy very, very quickly. I do apologize. So this is linear, and it occupies, say, like the x-axis. We want those unhybridized p orbitals to be perpendicular. Everybody's going to be perpendicular to one another. So if this is the x-axis, I'm going to have an unhybridized p orbital maybe on the z-axis coming out of the plane of the paper. And that'll happen on both of these since they both have the same hybridization scheme. So this is just one p orbital on this carbon. We got 1, 2, that's the 2sp, and right now I've just drawn in one p orbital. So we need a second p orbital. If this is x and this is y or z, then we're going to have another one in the third direction. They're all 90 degrees relative to one another. So this will be our second p orbital. We need to get those pi bonds in there, those areas of side-to-side overlap. So maybe I'll keep with the same colors. So this p will overlap with this p. It overlaps with the orbital that's on the same axis. So we have side-to-side overlap here. This is just, even though I've drawn two green lines, it's one orbital and there's only one bond. And this is going to be our pi bond. So that's one of the pi bonds. And then the one that's coming out of the plane of the paper, there's going to be some overlap there. So again, it's on both sides potentially. We don't really know where it is, but that's going to be our second pi bond. So to summarize, we have two hybrid orbitals, and those two sp hybrid orbitals account for our two sigma bonds. And then we have two unhybridized p orbitals, and that's going to be our side-to-side overlap with our two pi bonds. All the meanwhile, with these three areas of overlap, we've still maintained the 180-degree bond angle and the linear shape that we would expect for C2H2. So up to this point, we've seen combinations of S and P. We can also bring D into the mix, and that helps to explain expanded octets. How does a central atom accommodate more than 8 electrons? Well, if we hybridize 1 S, 3 Ps, and 1 D, then we're looking at 5 sp cubed D hybrid orbitals. And each one of them individually, if you're labeling a picture, would be sp cubed D. So for the example of a molecule that uses an sp cubed D hybridization scheme, I want to use PF5. So here's the Lewis dot structure, and there's a couple things to note here. It's the central atom, the phosphorus, that's going to take advantage of those sp cubed D hybrid orbitals. We have all these fluorines. I'm going to throw the fluorines into standard old p orbitals. And you might be wondering why. Well, look at the electron configuration for fluorine. We'll do helium, 2s2, 2p5. We got our 2s down here, our 2p right here. 2s2 is full, 2p5, we're almost full there. How many bonds does fluorine want to make? Fluorine needs one more electron. It wants to make one more bond. It has one half-filled orbital. So it's all set. It doesn't need to change anything in order to participate in bonding. So typically, for this reason, I keep my group 7 atoms in unhybridized orbitals. So just standard atomic orbitals. How can we recognize that a particular molecule is going to use an sp cubed D hybridization scheme? Well, it's going to be by the electron geometry of that central atom. So for here, if it's trigonal bipyramidal, then that's a good indication that it's sp cubed D. As I mentioned, we have 5 sp cubed D hybrid orbitals. That's it. There's no unhybridized orbitals around the phosphorus or around the central atom. And this will simply be 5 sigma bonds then, since we're just going to have one area of overlap with that phosphorus. Fluorine is going to use a standard p orbital, and since there's 5 fluorines, we can draw 5 p orbitals with end-to-end or sigma overlap with these hybrid orbitals. So everything drawn in pink is a p orbital, 2 lobes, and they all belong to fluorine. 1, 2, 3, 4, 5, and they all exhibit end-to-end overlap. And we can label all these areas of end-to-end overlap as sigma bonds. And these are the hybrid orbitals of the phosphorus. So for our last example, we want to look at something that exhibits octahedral electron geometry. The octahedral electron geometry comes from the fact that there's 6 hybrid orbitals. Along with, or because of those 6 hybrid orbitals, there will be 6 sigma bonds in molecules with sp cubed D squared hybridization. So for our last example of sp cubed D squared hybridization, we're going to look at SF6. So the sulfur in the middle uses the 6 hybrid orbitals. And each one of those hybrid orbitals will be labeled as sp cubed D squared. Then fluorine, because it's in group 7 and the situation looks good, it's got one half-filled orbital and it only needs to pick up 1 electron, we're going to put fluorine in the unhybridized p orbitals. And then last but not least, once we get all of the 6 p orbitals for the 6 fluorines in there, we can label them as sigma bonds. Sigma is end-to-end overlap.